What determines the force of friction? How accurate are our models of friction? These are the questions that we will explore in Investigation 5C, Static and Kinetic Friction. The force of friction on an object depends on the weight of an object and how sticky or slippery it is as it either sticks to or moves along a surface. We can calculate a coefficient of friction for two materials that are in contact. Your feet on a wet floor have a low coefficient of friction that might cause you to slip. My son used to say that his shoes had gription, a fun way to describe a high coefficient of friction between a shoe and the floor. In this investigation, your students will measure two kinds of friction. The force of static friction has a maximum just before the object starts sliding. The force of kinetic friction is the force required to keep an object moving at a constant speed. Your students have studied Newton's laws and learned about drawing free body diagrams describing the forces that act on an object. They will use these ideas to calculate the coefficients of static and kinetic friction for the friction block on the aluminum track and find out for themselves how accurate our models of friction are. For this investigation, each student group will need a track with feet, a smart cart with a hook, a friction block, two 250-gram masses, and string or thread. The groups will need to share masses so that they can record data with up to 4 masses, a total of 1 kilogram, resting on the friction block. Students should assemble their equipment as you see here. The friction block is tied to the Velcro end of the smart cart, and another string is attached to the hook of the smart cart. I have placed two 250-gram masses on the friction block. Once the cart is attached to the friction block, each group will open the experiment file, 5C, Static and Kinetic Friction, in SPARKvue, and then connect their smart cart using Bluetooth. Groups are now ready to begin recording data. Before recording data, students should zero the force sensor on the smart cart while nothing is touching the hook by clicking the zero button in SPARKvue. Students will start their data collection by clicking on the green button to start collecting data and pulling very, very slowly on the string, steadily increasing the force until the block starts to slide. Once the block is sliding, continue pulling the string at constant speed along the track and stop recording the data. When you look at the data, check for the following two features: a steady force while you're pulling at constant speed, and a peak just before the block starts to move. You can see when it begins to move on the position versus time plot. Students might need several tries to get both the peak and the steady force. I'm using the wood side of the block, which makes it easier to see a difference between the static and kinetic friction forces. You'll repeat the data collection 2 more times, each time adding a 250-gram mass on top of the block. These additional masses can be shared between groups. The data students collect includes force versus time, as well as position versus time. This allows students to see how the force changes as the block begins to move. They will need to find values for 2 forces from each run: the maximum force, which is the static friction force, and the average force while sliding, which is the kinetic friction force. First, I'll make the force measurement active, and then find the maximum force using the coordinates tool. Select the highest force value just before the block starts to move, and then turn on the coordinates tool. The average force can be found by selecting the data points for when the block was sliding at constant speed and finding the mean. Students then repeat this analysis for all 3 runs of force data. I've recorded the values for the max force and the average force while sliding in the student work table. Question A asks about the free body diagrams for the friction block just before it starts to slide and while it is sliding at constant speed. These 2 free body diagrams are identical. In both cases, the forces are balanced. There is no acceleration, either vertically or horizontally. Question B uses the relation between the friction force and the normal force to find equations for the coefficients of static and kinetic friction. We can use our equations from question B to answer question C. We use the values of max force and average force while sliding to calculate the coefficients of static and kinetic friction for each of our trials, and then find the average value. These values are similar to those of wood on aluminum from section 5.4 of your ebook. Your students can respond to questions D and E using their observations.